Good afternoon, students. Am I audible?
Yes, sir.
Yes, sir.
Okay. So just wanted to give you one update. So what I'm going to do is, there are two things, okay? Let me show you and explain. So what I will do is, initially, I'll be explaining the concept in this page, okay? After which, I'll give you some time for discussion session with respect to that particular topic. So what is the objective of this is, while I'm discussing this concept, I don't want anybody to speak. Okay, I don't want anybody to say yes sir or no sir unless I ask. Okay, if I ask, I will tell you. And while I'm writing here, I want everybody to make a note of it. At the same time, listen to me also. When this discussion session comes, you can unmute yourself and start speaking. So how much ever time you want here after the subtopic, you can take it. But during the time of discussion, I request you all to be silent, okay? Because this recording, I will edit it later and give it to you as a good quality content. So that is the whole idea, okay? So is that clear?
Yes.
Yes, sir.
Right? We'll get started. So first, we will start with a discussion session itself, okay? So everybody knows what chapter I'm going to deal with, right? What is it?
Wave optics.
Chapter 10, which is also called as wave optics, right? So in the previous lesson, we learned about ray optics, right? Then we know what is optics all about. So what is optics? Optics is a branch of physics that deals with light. Then how different is it going to be? How different is this wave optics going to be compared to ray optics? That's what we need to understand first, right? Any idea? So we know that optics deals with light and ray optics is the point. So we know that light is an electromagnetic wave. In that electromagnetic wave, we know that light is treated as a ray under certain scenario, and it is obviously treated as a wave under certain scenario. But what are the scenarios under which light is classified into two types, whether it is to be treated as a ray or a wave? How do we know that? Anybody? Okay. Now it is my turn. Right now, chapter 10, wave optics, which is also called as physical optics. Okay. So like how we saw in the previous chapter, ray optics was also called as geometric optics. In a similar way, when you talk about wave optics, it is also called as physical optics. Okay. So basically, optics is a branch of physics which deals with light. So optics is a branch of physics which deals with light. Optics is further subclassified into two types. One is called as ray optics and the second is called as wave optics. Right. So knowing this fact, we will try to answer. This is when light is interacting with objects whose size is comparable to the wavelength of light used. Means if light is interacting with those objects where you can compare the wavelength of that light with the size of the object, under that scenario, the branch of optics that is classified as ray optics. Similarly, when you talk about wave optics, it is a place where light is interacting with objects whose size is small compared to wavelength of light used. Means if the light is going to interact with very small obstacles like small openings, where those opening size is going to be very much small compared to that of the wavelength of the light that you're going to use, under that scenario, the branch of physics that comes into picture is wave optics. Please make a note of this point. Now, I'm going to explain you a small story of why this wave nature of light actually came into existence. Okay, there were certain theories which were proposed in the early stage itself, but since they didn't have proofs at that point of time, they couldn't prove it at that point. Hence, it took some time for the proofs to come out. Now listen to this. So first, there is something called as corpuscular theory of light. So basically, corpuscles are nothing but particles. So initially what happened, it was assumed that light did not have any wave properties and people thought it had only particle nature, and this was a theory which was first proposed by Newton. So what happened at that point of time is when Newton proposed it, he was a very big scientist where people started believing him. There was no counter for his statement. Okay, they started believing, yes, it had particle nature. But there came another scientist named as Huygens. Okay, Huygens, or some people call him as Huygens. So what he told is light did not possess particle nature, rather it had wave nature associated with it. Now the concept is, where did he get this idea from? That is, listen to this. Suppose there is a small opening and there is a wall. Okay, let's say this is the opening of a room and this is a wall. Now, if light rays are falling on this, right? If light rays are falling on this, had light been of particle nature, then what should have happened to all these particles? They would have gone and they will fall on the wall, means only this part of the wall would have been visible. But the important point that we need to note is, suppose you have a room where you have a window. Let's say this opening is a window. When light is going to enter through it, it is not only the wall which is, so on the wall which is opposite to the window, it is not only the area where the window is present is visible, but what will happen, you can see that even small parts above and below the size of the window will also be visible, where this is a phenomenon. So this phenomenon is called as diffraction. Generally what happens is, suppose let's say the door is closed and you're in this room and there is a person standing here and shouting. Okay, so if suppose they are shouting, what will happen is, when you're here, you might be or might not be able to hear them. But if I create a small opening like this, means let's say the door is slightly pushed like this so that there is a very small opening that is happening, then what will happen, the sound will travel through this and it will come and fall into your ears. Definitely compared to the previous scenario, in this scenario you are going to have a more intense voice that is reaching your ears. So from this we can conclude that sound is undergoing something called as diffraction. Diffraction is nothing but something similar to refraction only, but diffraction or diffraction, however you want to pronounce, it means that the wave will start bending when it hits an obstacle. Okay, so wave is going to start bending when it hits an obstacle, and this was the principle that was observed by Huygens, and he proposed the wave nature of light. But at that point of time, what happened is people were not ready to believe, because Newton was a big hand at that instant. Okay, it was later where certain experiments like Young's double slit experiment, Young's double slit experiment, then photoelectric effect. So all these experiments came into existence to prove that light had wave nature here and also it had particle nature here. So here what I did is I explained both the points. So the conclusion that I want to draw here is light does not have only wave nature. So wave nature of light was proven by a scientist named Thomas Young through an experiment called as YDSE, Young's double slit experiment. And photoelectric effect was the one which concluded that light had particle nature also. So this is the reason why we say light has dual nature associated with it. And that is the main objective of next chapter. Anyways, in this chapter, we are going to concentrate only on wave nature of light. Is that clear, guys?
Yes, sir.
Yes, sir.
Right? So I hope everybody understood the story. It is like what happened. Newton was there, Huygens was there. Newton proposed what theory? Corpuscular theory, and Huygens proposed wave theory. Right? So later, who proved it? It was by Young's double slit experiment that we came to know that light had both. The light had wave nature associated with it. Then came the experiment of photoelectric effect. So photoelectric effect, what did it prove? It proved that light had a particle nature. This is the experiment for which Einstein got a Nobel Prize, photoelectric effect. Many people think it is for the energy equation that he gave. No, it is not for the theory of relativity. It is for the photoelectric effect concept because this is the one which proved the particle nature of light. Is that clear? So I hope there is no doubt in this subtopic, right?
Yes.
Very good. So just give me a minute. No. Just a second. I'll be back. Right. So shall we move on to the next concept?
Yes, sir.
Yes.
Yes. Now listen, there are certain terms that I need to. Yeah. Now listen, there are certain terms that I need to introduce before we step into the Huygens theory. That is, you need to know a concept called as wavefront. Okay. Suppose there is a still water. What is it? It's a still water. In that still water, let's say I give you a stone and you're going to drop a stone into that still water. Then immediately I'm sure that you will observe something like this, where these circles keep traveling and the technical name given to these circles is called as ripples. Right? The water ripples are formed as a result of which you can see them traveling. Basically, what are they? They are actually waves only. So this is what you are able to observe in a medium called water. Now, sometimes what happens is when light is traveling from one point to another, we think that it travels in the form of rays. But what actually happens is light actually travels in the form of something called as wavefront. Let me explain what that wavefront is. So wavefront, the technical definition is something like this. So write it down. It is a continuous locus of all points. It is a continuous locus of all points which are vibrating in the same phase. So let me tell what it is. So a continuous locus of all points which are vibrating the same phase is what is called as a wavefront. That is a book definition. Okay, let me explain what it means. Suppose I have a point source. Let's say I give you an LED bulb, and that is the light source. From this light source, what will happen is you will have the electromagnetic waves that are coming out. Right? These electromagnetic waves will get liberated in all the directions like this. Because light is an electromagnetic wave of very high frequency and a smaller wavelength. Now let us look at what the definition has to tell us. So the definition says it is a continuous locus of all points which are vibrating in the same phase. What is the meaning of it? Means if I take a particular point. So let me explain what this phase is. If I take a wave like this, right? If I take a wave like this, phase is nothing but the angle. Okay. So at this particular angle, it has a particular value associated, like how you saw in the electromagnetic wave, how you saw it in the alternating currents chapter. We would have seen what is phase, right? Similarly, here also phase means angle. For that particular angle, we'll understand how much is the particles displacement. Okay. So if I take all those displacements at the same time, so let me draw a better diagram. Let us say this is the source and 1, 2, 3, 4, 5, 6, 7, 8, something like this. So let us say this is the phase of a particle at this instant. The same phase is followed here, 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 here. So if I join all these points, then the shape that I'm going to get, what is it? Then the shape that I'm going to get is what is called as wavefront. Okay. So this is the meaning of the book definition. Let me make it simple for you guys. Suppose the meaning of this is, if I have a point source, away from that point source, what is going to happen is light will start traveling in such a way that it will travel in the form of wavefronts like this. It will travel in the form of spherical wavefronts like this, so that the energy is transmitted from one position to another. So basically, what is a wavefront? It is a locus. Locus means it's a moving. Locus is a shape obtained by all the moving points. Locus of all those points which are vibrating in the same phase. Now let me take another example. Let's say I have a linear source of light. Okay. If I have a linear source of light, then each point on the source will act like a point for the light to get liberated. Each point on this linear source is also a source only, light source. So this will release a wave like this. This will release a wave like this. It will release a wave like this. So it keeps on going. So when it keeps on going like this, I can find one particular point which is common to all. That is the phase at which those particles are oscillating. So if I take something like this, right? If I take something like this on the other side as well, then I get a shape like this. So the shape that you're going to get here is going to look like a cylinder. Means what I'm trying to say is, when you have a point source, if the light source is a point source in nature, then the light will start traveling in the form of wavefronts which are spherical in nature. Suppose you have a linear source of light, then at that point the light will start traveling in the form of a cylinder. Similarly, if you have set of parallel rays, means if the source is placed at infinity, then the wavefront will look something like this, which are plane wavefronts. So these are the different types of wavefronts that we are going to deal with. We will be mainly dealing with spherical and plane wavefronts in this chapter for many theoretical purposes. Yeah. Is it clear, guys?
So can you explain once again for what conditions we'll get circle and for what we'll get cylinder?
What condition?
We'll get circular wavefront and
It's not
cylindrical.
circular, it is spherical. When you have a point source, you know what is the point source, right? A source which is very, very small, which is of the size of a point. At that point, what will happen is, let us say, see, for you to understand, let's say the rays are getting liberated like this, but these rays are nothing but waves only, right? So when these waves are there, there is a phase associated with it. Phase means there is a position of that particle, displacement of the particle at a particular instant. If you join all those points, you will get a shape. And that shape is mathematically called as a locus. In terms of physics, it is called as wavefront. Okay. So when you have a point source, you will get spherical wavefronts. What else is there? What else did I say? When you have a linear source, you will have a cylindrical wavefront. Wavefront is written with the symbol WF. Similarly, when you have a plane wavefront, similarly, you have a set of parallel rays. That is when the source is placed at infinity, then you will have these plane wavefronts. Okay.
Yes, sir.
Is that clear? Right. Is everyone clear?
Yes, sir. Yes, sir.
One minute. Okay. So the next thing is rays. Okay. So what are rays? An arrow drawn perpendicular to the wavefront is what we call it as a ray. So in the previous chapter, the definition of ray was an arrow mark which had a starting point but no ending point. Now we are trying to define the same ray in terms of wavefront. So what is it? If you draw an arrow perpendicular to the wavefront, then that is what is called as a ray. Okay. So there are two general principles that are involved in it. Okay. One is rays are always perpendicular to the wavefront. So what will happen is sometimes they'll give you the shape of the wavefront and ask you to draw the rays. What are you supposed to do? Just draw perpendicular to the wavefront at every instant. Second, the time taken for light. The time taken for light to travel from one wavefront to another, the time taken by the light to travel from one wavefront to another is the same along any ray. So what we are trying to say here is try to understand. If suppose I have two spherical wavefronts. So two spherical wavefronts are produced due to the point source. So sometimes what they will do is they'll give you the wavefront and ask you what is the source. Sometimes they'll give you the source and ask you what is the wavefront. Or what they can do is they can give you the source and wavefront and ask you to draw the ray. So at that point, what you should do is you should know how this ray is supposed to be drawn. That is, we know that rays are always perpendicular to each other. And the second most important point that you need to know is the time taken for the light to travel from one wavefront to another is the same along any ray. So we know that the rays are perpendicular to these wavefronts. So when you draw these rays perpendicular to the wavefront, then what is going to happen? They take certain time to travel from one wavefront to another. If you calculate the time taken by this wavefront and the time taken by this wavefront, they're trying to say that they both will be the same. That is the meaning of the statement. The time taken for light to travel from one wavefront to another is the same along any ray that you consider. That is the meaning of it. Okay. So these are the two general properties. Any doubt, guys?
No, sir.
So if you're clear, then I will go to the next concept. So the next concept is Huygens principle. Huygens principle of secondary wavelets. Okay. Huygens principle of secondary wavelets. So this is on the basis of wave theory. Okay. So basically what does it tell us? It tells how a wavefront propagates. Okay. And secondly, it talks something about secondary wavelets. Here, the important point that you need to understand is WF, wavefront, is different from wavelet. Listen to this carefully, you get the answer. Okay. So I will write down the statement, please copy it. The principle is based on the following assumptions. So this Huygens principle is based on the following assumptions. So first, each point on a wavefront acts as a secondary, each point on a wavefront acts as a fresh source of new disturbance. So acts as a fresh source of new disturbance, which is called as secondary waves or wavelets. So now read the statement carefully. What are they trying to say? Not what are they? What did Huygens principle tell us? Each point on a wavefront acts as a fresh source of new disturbance, and the new disturbance is what is called as secondary waves, or more technically secondary wavelets. So that is the first point. Okay, I leave some space. Second point. Secondary wavelets. Okay, secondary wavelets, underline this word. Secondary wavelets spread out in all directions. Spread out in all directions with speed of light in that medium. Okay, they will start spreading in all directions with what speed? With the speed of the light in the particular medium in which these wavelets are getting generated. Okay, and the third important point is the wavefront. Okay, I'll be more specific. The new wavefront at any later time, the new wavefront at any later time is given by the forward envelope, that is the tangential surface in the forward direction of the secondary wavelets at that time. So write down the statement. It is very, very important. I'll explain it. So let me explain each point. Listen to this. So the meaning of the first one is, let us say I have a point source. What do I have? I have a point source, and that point source is going to generate a wavefront, okay, which is going to be spherical in nature. It's not circular, it is a spherical wavefront. So each point on this first wavefront that is getting generated, that is, if you take individual points here, then these individual points will start behaving like n different point sources, so that they will start generating the wavefronts around them. Okay, they will start generating the wavefronts around them with themselves as the center. Then these wavefronts, which I have drawn in the dotted line format, are what are called as secondary wavelets. What are they called as? They are called as secondary waves or secondary wavelets. So try to understand. The first continuous line that I have drawn is a wavefront generated by the primary source. Right? Now, each point on that wavefront acts as a secondary source for that particular wavelet to get generated. Okay. The second important point is these wavelets are nothing but their light only again. So these secondary wavelets, what they will do is they will start making the circle, that is the radius of that circle will depend on the speed of the light in that particular medium. These wavelets will start growing in the circular form depending on the speed of that light, in that medium. That is the meaning of the secondary point. That is the meaning of the secondary point. Sorry, second point. So secondary wavelets spread out in all directions with speed of light in that medium. And the third most important point is you have drawn the first wavefront, you have drawn the secondary wavelets. Now the question is, how is the new wavefront generated from these wavelets? So if we repeat the story again, then I am clear that if I have a spherical wavefront, on that spherical wavefront, I will take multiple dots like this, and these dots act as a source. Not only these dots, every point on this acts as a source only. And the light will start spreading with the speed of the light, with the speed of it in that particular medium. So once you get the secondary wavelet, observe what is the point saying. The new wavefront that is required at any later point means, let's say the speed of the light in that medium is v. After a time vt, this wavelet would have generated a radius of vt. This wavelet will also have the radius vt. This will also have the radius vt. This will have vt and this vt according to the second point. Now, according to the third point, the new wavefront at any later time is given by the forward envelope. So what is that forward envelope? It is nothing but the tangential surface drawn in the forward direction of the secondary wavelets at that time. Means if I take these wavelets to these wavelets, if I'm able to draw a tangential surface like this, then if I join it like this, then this tangential surface drawn for the secondary wavelets is what we call it as the new wavefront. Okay. So this point is very, very, very important for you to understand the subsequent concepts of the loss of reflection and loss of refraction, which we will be proving using the wave theory of light. Guys, is it clear? Any doubt?
Yes, sir.
Is every point clear? That is very, very important. Okay. Is every point clear? I'll show you if you want. You can just go through it, take a minute time. If there is anything that is not clear, please ask me. I hope you guys have written it along with me. Yes, guys. Only one girl has responded. Everyone else, are you people
Yes,
clear?
I understood, sir.
Very good. Very good. Okay. So can we move on to the tougher part? Here comes the tougher part of this chapter. Okay. One minute. Yeah. So the next important concept that we are going to see is reflection of light. Reflection of light on the basis of wave theory of light. So please concentrate. Let us say I have considered a reflecting surface. On that reflecting surface, there are two parallel incident rays that are going to hit. Okay. So when I say parallel rays, these rays are coming from a source at infinity. So for the source at infinity, what is going to be the shape of the wavefront? We already know. Source at infinity will have plane wavefronts. So when these rays are hitting here, what will happen at this point is I can take a wavefront which is perpendicular to the first incident ray. So what did I do? I took a wavefront which is perpendicular to the incident ray because we know the fact that rays and wavefronts are always perpendicular to each other. So when I do this, so if I call this as the first ray and if I call this as the second ray, then I'm clear with the fact that the second ray had to travel some extra distance after the first ray had hit the surface. So if I take this is t is equal to 0. So the instant the first ray is hitting the reflecting surface, if I call it as t is equal to 0, I'm sure if I start the stopwatch at that instant, then the second ray is definitely going to take few more seconds or few more milliseconds or whatever it is extra compared to the time taken by the first ray to hit. So in that time, what would have happened is the first ray would have started building an incident wavefront, right? So now what will happen is, now comes this theory. Each point on the wavefront acts as a source of new disturbance called as the secondary waves or wavelet. So the wavefront is already formed, right? So the wavefront is already formed. From this wavefront, what will happen is there will be wavelets which are getting generated like this, right? when they are getting generated in this extra time t, the point which is at the first point of incidence, at this point of incidence, would have generated a ray, would have generated a wavelet of radius v into t. It would have generated a wavelet of radius v into t, which is going to be in this direction. I'll draw it again. Observe. Reflecting surface, first incident ray, and let's say this is the second incident ray. Okay, so by the time the first incident ray hits the surface, it would have started generating wavelets. So if I calculate this distance Vt, okay, where V is the speed of the light in that medium and T is the extra time taken by the second ray to hit the surface, what would have happened is the first ray would have already generated a wavelet. Let's say this is the wavelet that it has generated. Okay, so from the second point of incidence, if I draw a tangent, to this, wavelet, then this will be the reflected wavefront. Okay, and to this reflected wavefront, if you are able to draw a perpendicular from the first point of instance like this, then this becomes the reflected ray. So if you observe, what I did here is, it is actually a geometrical construction which I took, like how you have some steps to be followed, right? Draw a line segment of this much value, then from there draw the perpendicular bisector, all those things. In a similar way, in physics, what I did is I took the concept of Huygens principle of wave theory and I've tried to draw this particular construction through which we got this kind of a diagram. So if you observe, this will be the incident ray and this will be the reflected ray. Okay, so when this is going to be the reflected ray, then what I will do is, to the second incident ray, I will draw a reflected ray which is perpendicular to this reflected wavefront. If I do this, then if I draw a normal at this point, listen to this carefully. If I draw a normal at this point, then this is called as the angle of incidence and this is called as the angle of reflection. So when this is the angle of reflection, then what will happen is this will be 90 minus r. When this is 90 minus r, this will be r. Okay, similarly, this is I, then this will be 90 minus I, then this will be I. So what is going to happen is, I'm going to consider two triangles and prove that angle I is equal to angle R. Okay, the triangles that I'm going to consider are, listen to this. If I take this point as A, this point as B, if I take this point as C and this point as D. Okay, 1 minute. I need to take this point as A. So if I take the triangle ABC, if I take the triangle ABC, and if I say this angle is I, and if I take the triangle DBC. If I take the triangle DBC and if I say this angle is R, okay. When I say that these two angles are R, now observe, this is reflected ray and this is the reflected wavefront, so they both are perpendicular. Similarly, this is the incident ray, this is the incident wavefront, they both are also perpendicular. So angle A is 90, angle D is 90 degrees. And I can say BC is a common side for these two triangles. Right? When BC is going to be common, then what else can I say? Then I can say AC is equal to BD. Because AC is VT, BD is also VT because you took that as the radius and drew it. So what are we trying to do? Angle A is equal to angle D is equal to 90 degrees. BC is common side and AC is technically equal to BD. So what we can conclude is that these two triangles are congruent. When these two triangles are going to be congruent, we know that all the angles are supposed to be equal. From this, we can conclude that angle I is equal to angle R. Okay. So from this, we will get the laws of reflection. So this is how the laws of reflection are proved on the wave theory of light. Okay. Yeah, now you ask. What questions you?
In the diagram, I have a doubt.
In the diagram?
I have a doubt in the diagram.
Yeah, sure.
So you marked one reflected, one for the first tracer, you've given it as reflected wavefront, and the other one you given reflected
I'll
wave.
show you. I'll show you the diagram again. Follow the steps. Okay. First, what are we doing? Reflecting surface. What is this?
Incident.
This
Parallel to the first.
parallel incident ray. So this is the first, second. So you imagine you throw a stone into this water, then what will happen? That stone will start generating wavefronts. So it started generating wavefront like this.
Yes, sir.
Right. So what is the name of this wavefront? Is this incident wavefront or reflected? It is incident because this wavefront is perpendicular to the incident ray. Rohan, are you able to understand? This is the incident. It is the incident wavefront. Okay. So this incident wavefront is perpendicular to the secondary also. But when I try to cut it parallelly, I'm able to understand that the secondary has traveled an extra distance of VT. Correct? So by the time the second stone takes to hit the water surface, the first stone would have started producing ripples. Are you able to understand? So this has already created this disturbance. So water particles are traveling like this in the form of ripples. So in that extra time t, what would be the radius of the wavelet that the first source would have generated? It will be, so if I draw this radius, how much will be the radius? That radius will be Vt. Why Vt? Because Vt is the extra distance traveled by the secondary before creating the disturbance. So both are happening simultaneously. Try to understand. The secondary is still traveling, but the first ray has already hit the water, hit the reflection surface, and it has started generating the disturbance. Correct? So what will happen is, from the second point of incidence, if I draw a surface tangential to the wavelet, if I draw a tangent to the wavelet, what will I get? According to the third principle of Huygens, a tangent drawn to the wavelet will give you what? Tangent It will give us the new wavefront. Correct? So you got a new wavefront, and that new wavefront is what is called as a reflected wavefront. Okay. So to that reflected wavefront, from the first point of instance, if you draw a perpendicular, so reflected wavefront and reflected ray are perpendicular to each other, accepted?
Yes, sir.
Then what is this? This will be the reflected ray. Correct? So to this, I'll change the color. See, to this reflected wavefront, if I draw a perpendicular at the second point of instance, what will I get? I'll get an other reflected ray. So this reflected ray is from the first reflection incident ray. This reflected ray is from the second incident ray. Is it clear?
Sir, understood. Yes, sir.
Now this angle will be R. This angle will be I. Remaining is mathematical expression. Okay. So don't worry much about this because I've already done a video on this with a clear-cut diagram. I've used compass, protractor, and everything. I've showed it. Okay. I'll be uploading in the app today. You guys can go through it later. What I suggest is you make the notes according to the way I drew it there and try to relate it to the concept that we discussed today. Is that okay?
Yes.
Will that work? Okay. So work on that. In a similar way, what I will do is I'll share the video of the refraction also. You go through that concept and come so that tomorrow my job will be easy for you guys. Okay, you'll understand things better. Okay. So since this is a slightly tougher concept, I'm stopping with this. Okay. I want you guys to work on this and come. Maximum 3 more classes, we are done with this chapter. Okay. Any other doubts from today's class? Any other doubts? Right? Okay. Sorry?
No doubt, sir.
No doubt. Okay, very good. Okay, then we'll wind up. Okay, I'll see you all tomorrow.
Thank you, sir.
Tomorrow
Thank
you have school. Like in the sense any online celebration, something?
Not sure.
Not sure, sir.
Nothing is announced, right? Okay, if there is no school, tomorrow we'll be having a morning class. I wanted to say.
Okay.
Okay.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.